The research goals of this study are to promote cellular apoptosis within cancer tumors, increase reactive oxygen species in cells, and increase the solubility of an existing cancer drug, piperlongumine, via replacement of the trimethoxyphenyl group with ligustrozine right here.
All right, so the first mechanism of our experiment is a Vitti-Corner reaction. Before we can show you our candies, we gotta show you what they are. So green is for nitrogen, orange for oxygen, red for sodium, pink for hydrogen, yellow for phosphorus, and these Skittles, these are gonna be our electrons. Okay. So the first step of a Vitti-Corner reaction, you have to create your Wittig reagent. Unlike a regular Wittig, you start with a Wittig reagent. To create our Wittig reagent, sodium hydride, so sodium hydride, is going to attack this alpha proton. So when it attacks, it takes off this hydrogen, they're going to form hydrogen gas. This bond here bends in, and when he bends in, this double bond, this pi bond, bends up. And that bending up will put another set of electrons on our oxygen molecule up here. When he has 6 electrons around him with his bond to the phosphorus, he's going to be negatively charged. So this Wittig reagent is now ready to attack our molecule. Okay, now with our Wittig reagent, this pi bond here that's attached to the phosphorus is able to come over and attack our molecule, which is going to cause this carbon bond to come back and attack its phosphorus. This whole entire, this 2-arrow reaction is what's going to form our oxophosphate intermediate. Okay, now that we have our oxophosphate intermediate, our box structure here is going to decompose so that we form our new molecule. So the bond right here is going to break and he's going to come down and attack him. So we get a double bond there. Because of that, this bond is going to break and fold up. This gives us our 2 products. This is the product that we were going for in our entire mechanism, and this is our side product formed from our Wittig reagent. Taking the molecule we created with our Vitti-Corner reaction, and we're going to be performing an ester hydrolysis with it. The first step of this ester hydrolysis, we're going to be taking lithium hydroxide, and for this reaction, instead of using red as sodium, we'll be using red as lithium, and instead of using yellow as phosphorus, yellow will be chlorine. So with our sodium hydroxide, what happens in sodium hydroxide is it's going to dissociate, and when it dissociates, the oxygen is now going to be ready to attack this carbonyl. When it attacks this carbonyl, 2 of the electrons will attack it, and it's going to break this pi bond, and that breakage of the pi bond is going to put another set of electrons on our oxygen, and it's also going to attach our alcohol group, which will look like that. All right, so next what our molecule is going to do is it's going to reform its carbonyl. So this negative charge is going to go down, it's going to attack, reforming the carbonyl. When it reforms the carbonyl, it's going to kick out our leaving group. And that just reshapes the molecule so that it will look like so. So this is the molecule we were shooting for with our ester hydrolysis, but because there's still lithium hydroxide dissolved in the reaction mixture, the lithium hydroxide isn't done yet. So what the lithium hydroxide, still dissociated, is going to do is the oxygen is going to steal this hydrogen off of the alcohol group here, and that's going to make a little water molecule. We're just going to bend this in, and when he bends in, we get 2 more electrons here, and now we got a negative oxygen, which we're going to have to treat. To treat our molecules so that we get our alcohol group back on, what is going to happen is we're going to add hydrochloric acid. So this is our chlorine, this is our hydrogen, and what's going to happen is our negatively charged oxygen is going to see this proton, and he's going to snatch him, which reforms our alcohol molecule, and then this will bend in so that he gets his molecule, and then we'll just have a negatively charged chlorine atom. So then you get your final molecule for this process. Alright, so for our third and final mechanism, we're going to be showing the formation of alkyl chloride, which is then going to be replaced with an amide. So to set this up, we're going to have triethylamine, which is a base. He's going to attack our alcohol molecule. When he does, he's going to steal that a proton. Just going to set these guys on here, and then we have a negatively charged oxygen molecule. So now our negatively charged oxygen is going to bend in. When the negative charge is going to bend in, it's going to form a pi bond there, which is going to cause this one to want to form a bond over here with pivovoyl chloride. And when that bond forms there, that's also going to knock this bond up, which causes that oxygen to be negatively charged. Because when it attacks there, that is going to form a bond between this oxygen and this carbon. So now that we have this chlorine here, this chlorine makes a great leaving group, and because of that, this negatively charged oxygen, two of his electrons, the negative charge is going to bend in, and when it bends in, makes a pi bond there, which knocks off this chlorine, who's now going to be negatively charged. So now that we have this negatively charged chlorine ion is actually going to come in and it's going to attack this pi bond right here, this carbon, which is going to break this pi bond and form a negatively charged oxygen, and it's going to attach this chlorine to the same carbon, like so. Before we're able to attack our acyl chloride, we need our amide group ready to go. And our amide group, we want to be a strong nucleophile. So to create a strong nucleophile amide, what we're going to do is we're going to use N-butyllithium, and then N-butyllithium is going to steal the hydrogen off of our amide. Just going to fold this bond in, which is going to create a negatively charged nitrogen, and that is our strong nucleophile. Our strong nucleophile amide, what it's going to do is it's going to attack this carbon right here, and that's going to fold out that bond, and creates our negatively charged oxygen, and it's also going to form a bond between our amide and our molecule. So our last and final step is to once again reform the carbonyl, and then we're going to use chlorine, our strong leaving group. We're going to kick him out. So he's going to be negatively charged, and that will fold up the amide so it sits there nicely, and that will be our final product.
The study was important in finding promising results in decreasing cell growth, decreasing tumor size, increasing life expectancy, and finding new treatment options for expanding into reactive oxygen species.